Okay, in this next set of numbers, we're given, well, numbers, and we're asked to kind of do the same thing we did in the last example. We're asked to organize it and draw some sort of picture that's appropriate for this type of data. So the first question is this qualitative or quantitative? This time we're dealing with numerical data, so we definitely would fit that under the quantity category, so it is quantitative. And as far as the y goes, because we are measuring numbers. Then we are asked to make a frequency distribution using 10-point bins. Okay, so 10-point bins in this case just simply means go into our data and just make sure that there's gaps of about 10. So what we're going to end up doing is we're going to say that 99 to 90, and 89 to 80, and 79 to 70, that those are a gap of about 10 numbers. So you're probably thinking, wait a second, why isn't it 90 versus 90 to 100 and 80 to 90? And the reason being is that let's say my number is 90 or my number is 80, I have to have a clearly defined spot that only contains one value. So I can't put 80 in two places. So I just need to make sure that it goes up to a particular value. 69 to 60. Okay, so you can kind of see how this goes. And 29 to 20. Okay. Now I need to go in and organize this. So anything with a 9 on it, I'll count in that first column. So 1, 2, 3, 4, 5, 6. So I have a 6 there. Anything with an 8 on it, so 80 something. 1, 2, 3, 4. So we got 4 in that category. Anything with a 7, so 1, 2, 3, 4, 5. 5 in that category. Anything with a 6, 1, 2. Anything with a 5, 1, 2. That's it. Anything with a 4, so 47. And then anything with a 30. Okay, and it's okay if there's a gap or a hole there. That's actually does tell us something about our data. Okay, so there's our frequency distribution. Next up is to draw a histogram. And I can see that the highest I go up is 6. So 2, 4, 6, 8. Kind of separate out that way. Now with histograms is a little different as far as how I label the box. So in other words, there's a natural order to this and I have to label it correctly. Because I went from 20 up to 29 and 30 up to 39, when I label my bins, I want to make sure that the bottom of the rectangle and the top of the rectangle are surrounding a common number. And the easiest way to do that is just pick 5. So if I put 25 to be the center of 20 to 29, and then 35, and then 45. So when I might label this, I'm just sort of picking that midpoint in between my bins to label where I'm going to put the rectangle. 85, 95, okay. And then I just draw a connected rectangle. So 25 had nothing. 30 to 39 had 2, so just to make sure that's a nice sliver of that. And so that right there would be our 30. And we're saying that right there is 39. But it's touching the next bin up. So 49 to 40, that'd be a 1. This would be a 2 again. That's another 2. 70 puts us up at 5. And again, I'm not going to pull a ruler out and measure these things. I'm just going to look and visually see that they're of different heights. And then 6 on this last one. Okay, So that's what our histogram now looks like. Number 14, would you expect a positive, negative, or no correlation between the following variables? So in this case, we're sort of identifying whether positive means as one gets bigger, the other gets bigger. Negative is one gets bigger, the other gets smaller, and no correlation means ain't nothing going on there. So the two quantities we're measuring, number of hours worked, an hourly wage, and the size of the paycheck. So this one to kind of think about. If my hours work go up, what would I expect my paycheck to be? I would expect it to go up. So I would expect there to be this positively trend line. So positive. As I work more, I expect to get paid more. All right, second scenario, number of cows and the number of citizens who've earned a PhD. So as the number of cows get bigger, is there any expectation on how many PhDs are out there? I'm going to go ahead and say that no. There's, I'm not sure if it goes up or down. It's a little confusing as far as what the pattern could be. So this would be an example of no correlation. Because I would not expect to see a pattern between cows and PhDs. It'd be one of those things in real life that would be a really big shock if I saw something like that. Number 15, 16, and 17, we're given the set of data and we're asked to sketch a scatter plot and then answer some questions about it. Okay, now I do want to emphasize that this is a very rough sketch. And since I can't get, I'm just going to do it off the side here. So this might be something where maybe you want to type it in to Excel and get it to create a picture for you. Or if you want to use your calculator, I'm just going to do a rough estimate by hand. Looking at the heights, looks like the lowest is 62 and the highest up to 70. So if I just go 60, 65, 70, 75, and 80, and then GPA looks like we're going anywhere from 2 up to 4. So 2, 3, and 4. And then I'm just going to plot estimated points. So 68, 3.75 would be about there. 62 and 2.1 would be there. 67 and 3.4 would be right about there. 78 at 4.0. And 72 and 3.75. Okay. So there's my rough sketch, and that's about as good as I'd expect to see, something like this. So that's number 15. I'll label, let's see, height goes here, and GPA goes on the vertical. Does a correlation exist, and if so, is it positive or negative? Okay, so as I look at it, it looks like there's a positive trend. I'm sorry, I'm writing that all sorts of, that goes down there. That's number 16. Is the relationship between height and GPA a coincidence, the result of some common underlying cause, or the result of one of the variables actually being the cause of the other, and then give some sort of explanation? Okay, so in this case, I hate to say the idea of common sense, but as we're looking at this trend, clearly, according to this data, there is a trend to be taller makes you smarter. Now, in real life, does that have any value or merit to us? Does it make sense that taller people are generally smarter? Well, it kind of depends on your own height, isn't it? If you consider yourself tall, then I imagine, yes, you would say that that's true. But generally speaking, I think it's just a coincidence for this particular data set. I can't think of any good reason why tall people would be naturally smarter than another. So I'm going to say it's a coincidence because height and GPA generally are not connected. Number 18, suppose you have a bike lock with 4 dials. Each has 10 letters on it. How many different potential combinations does your lock have? Even though it says the word combination, it is not an example of a combination. It's actually an example of a permutation. But moreover, it's the multiplication principle. So if there's 10 letters on it, that means each has 10 letters on it. So that means we've got 10 options for each choice. And it's possible to have this, so we could have like AAA. It could be the same number repeated, or letter repeated. There's no indication that one has to be different than another. So there's 10 choices for the first position, 10 choices for the second position, 10 for the third, and 10 for the fourth. And that's actually good enough to get you full credit, by the way. You don't necessarily have to multiply it out. Number 19, suppose you roll 2 6-sided dice and then add the numbers on the dice. What is the probability that they will have a sum of a 7? Okay, so what we have to first think of is when I roll 2 dice, what are the possibilities that will generate a 7? So it could be a 1 and a 6, or a 6 and a 1. Could be a 2 and a 5, and a 5 and a 2. Could be a 3 and a 4, and a 4 and a 3. And that's about it. So there are 1, 2, 3, 4, 5, 6. There's 6 ways to get a 7. If you remember from our notes, there are 36 possibilities as far as if I routed all the different combinations. So there are 6 out of 36 ways to get it, or 1 out of 6. It is okay to reduce in this case. Number 20. If one card is drawn from a standard deck, what is the probability that it will be red? Alright, so at this point we need to think about how many cards are in a deck. There are 52 of them, and exactly half of them, or 26, are red. So 26 out of 52 is fine, or 1/2 is fine. Number 21, suppose you flip 4 coins and then count the number of heads. Make a probability distribution listing all possible events and their probabilities. Okay, so we're going to make a table here. So we're going to talk about an event and the probability of that event. Okay, so we got the event of 4 heads. We got the event of 3 heads. We got the event 2 heads, 1 head, and 0 heads. Okay, now first question to sort of think about is how many different possibilities are there? Well, it's either heads or tails, and there's 4 coins total, which means all of my illustrations would be 2 to the 4th, so there's 16 possibilities. So I can go in right now and I can put denominators of 16 on all of these choices. Okay. Now, there's going to be some nice patterns that are going to make this a little bit easier for us to figure out. So, for example, 4 heads, how many ways can 4 heads? It's just H, 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 H. So, of the 16 possibilities, there's only 1 of the 16 that fit that. Similarly, if I have absolutely no heads, there's only one way that'll happen. That's 4 T's, T, 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 T. So 1 out of 16 for that. Now, 3 heads and versus 1 head is kind of the same question. 3 heads, I could have the t first, and then HHH. I could have the t second. I could have the t third, and I could have the t fourth. So there's only 4 ways for that to even show up of the 16 possibilities. So there's 4 there. And similarly, if I switch t's with h's, there's only 4 ways for 1 head to show up. It's kind of the same thing with 1 tail to show up. Now at this point, rather than sit there and think creatively about, well, let's see, if I had 2 heads, would be I could have the heads first, I could have an H and then a T and then an H. And instead of sitting there thinking of that, let's kind of understand that all of this has to add up to 1. 1 over 16, 4 over 16, 4 over 16, all of that all those fractions have to add up to 1, or more specifically, the numerators have to account for 16 possibilities. So how many possibilities have I taken care of so far? I got 1 and 4, so I got 5 there. 4 and 1, so I got another 5 there, so I got 10 of 16. So that means that the other, the 2 h's has to be 6 out of 16. And usually that's about the easiest way to do this, is sort of think about what's missing from the add up to 1 and put that in for the missing fraction.